Hello, everyone. Welcome back. We are in the second and final lecture of Chapter 4 of Fundamentals of Inorganic Glasses. Chapter 4 is about microstructural evolution in glasses. As we know, most glasses are chemically homogeneous and therefore are lacking in a microstructure. But what we learned last time is that it may be thermodynamically favorable in some cases for the glass-forming liquid to exhibit liquid-liquid phase separation, which could lead to spinodal decomposition or droplet nucleation and growth, in which case there are actually two liquid phases that give us two different glassy phases that have a certain type of microstructure, either this droplet and matrix type of microstructure or the interpenetrating phases of spinodal decomposition. Today, in this second lecture of Chapter 4, we are going to deal with microstructural formation by controlled nucleation and crystallization. And it is through this controlled nucleation and crystallization that we can convert a glass into a glass ceramic. This is a process which is known as ceramming. If someone says that they're going to ceram their glass, what that means is that they're going to put it through some sort of a heat treatment cycle in order to have controlled nucleation and crystal growth, to have crystals that form within the glassy matrix. And the reason that this is done is that glass ceramics, with their combination of crystalline properties and properties of the remaining glassy matrix, these glass ceramics can achieve properties that are superior to that of the native glass itself. And also the processing of glass ceramics can be easier compared to traditional ceramic processing. So let's jump into it. First thing is to recall from 2 lectures ago, back at the end of Chapter 3, we were covering the kinetic theory of glass formation. Remember that this kinetic theory of glass formation states that any liquid can form into the glassy state, provided that you cool it fast enough to avoid crystallization. And we studied this in terms of classical nucleation theory. With classical nucleation theory, we developed this rate of homogeneous nucleation. And if you remember, there was a trade-off here between thermodynamic and kinetic effects. So this figure on the right shows temperature versus the rates of nucleation and crystal growth. And what we see is that this Tm here is the melting temperature. At the melting temperature, the rate of nucleation is 0. And then below that, below the melting temperature, there is an increased thermodynamic driving force for nucleation. That is because there's an opportunity for the liquid, in this case, the supercooled liquid, to lower its Gibbs free energy by undergoing a phase transformation from a liquid to a crystal. And so the lower that the temperature is below the melting point, the greater the thermodynamic driving force for nucleation, because there's greater and greater thermodynamic benefit to nucleating crystals. And therefore, the nucleation rate is increasing as the temperature is lowered. But then it goes through a peak at some point, and then the nucleation rate starts to decrease as the temperature is lowered even more. And this is because the kinetics of the nucleation process are becoming exponentially slower at these low temperatures. And so where we have this peak, this is really an ideal trade-off between having a sufficiently large thermodynamic driving force for nucleation and also sufficiently fast kinetics to see it happen. All of the temperatures above this peak temperature are said to be thermodynamically limited, and all of the temperatures below that peak are said to be kinetically limited. And so the peak of the nucleation rate occurs where we have this ideal trade-off between thermodynamic and kinetic effects. If we are trying to avoid nucleation, say if we're trying to make a nice glass without any crystals in it at all, what we need to do is to cool the system fast enough through this region where nucleation or crystal growth is likely in order to suppress nucleation and crystal growth. However, if we are making a glass ceramic, we want to be able to control the amount of nucleation and crystal growth, and that would usually involve doing a first heat treatment here at this peak nucleation temperature in order to develop nuclei or to develop a desired population of crystal nuclei within the glassy matrix itself. Now, the other process, the second process that leads to crystallization is the crystal growth process. Remember that crystallization occurs in two steps, where first there is nucleation, and once a stable nucleus forms, that stable nucleus can grow into a crystal via the crystal growth process. And in order to get crystallization, we need to have both of these steps. And they must occur in this order. First, nucleation, followed by crystal growth. With the crystal growth rate, again, at the melting temperature, the crystal growth rate is 0. And that's because by definition, at the melting temperature, the Gibbs free energy of the liquid state is equal to the Gibbs free energy of the crystal state. So there's no thermodynamic driving force for crystal growth to occur. If we are at temperatures above the melting temperature, the crystal growth rate becomes negative, and that's because it is thermodynamically favorable for the crystal to melt, so to convert from the solid crystalline state into the liquid state at temperatures above the melting temperature. And that's what gives this negative crystal growth rate at temperatures above Tm. At temperatures below the melting point, we develop a similar type of trade-off between thermodynamic and kinetic effects as compared to what we get with nucleation. As we lower the temperature below the melting temperature, there's a greater thermodynamic driving force for crystal growth to occur because there is a greater lowering of the Gibbs free energy after undergoing the phase change from the liquid state to the crystal state. Then we go through a peak. That peak occurs at the temperature where there is an ideal trade-off between thermodynamic and kinetic effects for crystal growth. And at temperatures below that peak, we are kinetically controlled because of the exponentially slower kinetics of taking atoms or molecules from the liquid state, crossing that boundary between the crystal and the liquid, and getting them incorporated into the crystal state. Now, one of the things that you'll note is that this ideal trade-off here, the peak of the crystal growth rate, occurs at a temperature that is higher than the peak nucleation rate temperature. And the distance between these two kind of governs how good a glass former that the particular liquid is. If there is a really large separation between the nucleation and the crystal growth curves, that means that there would be very little overlap between the two, which means that it would be easier to form a glass because it's easier to suppress crystallization, since this needs to occur by first nucleation and then crystal growth, but the peak nucleation rate is occurring at a lower temperature compared to the crystal growth temperature. So if we're taking a liquid, let's say starting at the melting temperature and then cooling it down, first it sees the crystal growth rate, and then it sees nucleation. But we know that these processes have to occur in the other order, where it's first nucleation and then crystal growth. So if you've got a really large separation between the two, that is actually very effective for suppressing the overall level of crystallization in the system. However, on the other hand, if we do have a large overlap between the two, such as in the shaded region shown here, in this shaded region, this is where we have both an appreciable amount of nucleation as well as an appreciable amount of crystal growth. And so in this shaded region, this is where we can have the two processes happening at the same time. And this is kind of the dangerous region if we're trying to get a glass. And if we're trying to get a glass ceramic, this is where we've got both the nucleation and crystal growth processes happening together. So this curve is really critical, both to understand how we can get a glass by suppressing nucleation and or crystal growth, but it's also critical for understanding how we get glass ceramics, because with a glass ceramic, we want to control both the volume density of crystals as well as the size of those crystals. And therefore this involves taking a glass and putting it through heat treatments at both the nucleation temperature here, Tn, as well as the crystal growth temperature, Tgr. An example of this is shown on the plot on the right, where we start off with our glass-forming liquid here at melting temperature Tm. This undergoes some sort of a forming operation in order to get the shape that we want the glass and ultimately the glass ceramic to have. But then this glass product is held at the nucleation temperature. This is at or near where we get this peak nucleation rate, where there's this ideal trade-off between thermodynamic and kinetic effects for nucleation. The longer that we hold the glass at this nucleation temperature, the greater the density of nuclei that will be formed. So if we hold the system here for a long time at the nucleation temperature, that means we have a larger number of nuclei per unit volume, which means that ultimately we're going to have a greater number of crystals per unit volume. On the other hand, if you hold the glass at the nucleation temperature for only a short period of time, then we have a lower density of nuclei that form and ultimately a lower density of crystals in our final glass ceramic. And the idea is that after we have stayed at this nucleation temperature for the desired amount of time in order to get the desired population of nuclei, then we heat this back up to where the maximum crystal growth rate occurs, this TGR, or this growth temperature. And the longer that we hold the system at this growth temperature, the larger the crystals will get. So every one of the stable nuclei that forms during this nucleation heat treatment step, every one of those stable nuclei are going to grow into crystals. And the longer that we hold the system at this growth temperature, the more time there is for atoms from the liquid matrix to cross that boundary to the crystals, be added to the crystal, and therefore grow the crystals. When we are done growing the crystals, when they have achieved their final desired size, then we cool the system back down to room temperature, and we have a frozen end microstructure. This microstructure is a glassy microstructure with crystals embedded within that glassy microstructure. Now, the number density of crystals is really governed by this nucleation step, because this is telling us how many stable nuclei that we get per unit volume. And then the size of those crystals is governed by how much time we spend at the crystal growth step. And so by independently controlling the amount of time that we spend at the nucleation step and at the crystal growth step, we can control the microstructure of our glass ceramic by controlling the population density of nuclei, and then the size of the crystals that form. And glass ceramics can range from anywhere from having like a small number of nano-sized crystals, where it's mostly a glassy matrix with some very small nano-sized crystals embedded in them, or they can range all the way to having almost no liquid or glassy state remaining, with almost the entire system being a crystal. And so anything in between is also possible. Now, one of the major advantages of glass ceramics compared to traditional ceramics is the ease of forming glass ceramics. Now, traditional ceramics are usually made via a powder sintering route, where you take powders of the material and then they need to be pressed into a green body. That green body has a lot of porosity in it, and the goal then is to eliminate as much of that porosity as possible by having this porous green body undergo a sintering process. That sintering process involves applying high temperature, sometimes also higher pressure or some elevated pressure, in order to evolve the microstructure of the glass ceramic to eliminate the porosity. In practice, though, it's impossible to completely eliminate the porosity from ceramic bodies. There's always going to be some small amount of porosity that's left that could compromise some of the mechanical properties of the glass of the ceramic, or optical properties or other properties of interest. With a glass ceramic, one of the key advantages is that the shaping and the processing of this material is done in the liquid state, not in a powder state or a solid state. And what this means is that we can run our glass factory through exactly the same steps that we would undergo for making glass products, for making glass ceramics as well. So we can shape, say, a glass bottle or a glass sheet or whatever shape we want. This can be molded or formed in the liquid state using liquid state processing. So in that case, there is no porosity. And in fact, in most glass ceramics, the amount of porosity is zero because of this liquid state processing. Then we take the glass that is formed. So whatever forming that takes place is done in the liquid state. It gives us this glass article. That glass article is then subjected to the nucleation step and then the crystal growth step to develop the crystal microstructure within that glassy matrix, completely bypassing the need to eliminate porosity via sintering or to undergo any type of solid state processing. So there's some definite processing advantages of glass ceramics compared to traditional ceramics. Compared to traditional glasses, glass ceramics can offer improved properties, say with respect to mechanical strength, mechanical toughness, lower thermal expansion coefficient. So there can be a lot of advantages of glass ceramics over glasses as well. This shows a few examples of glass ceramic microstructures, and the number of microstructures that you can get is rather unlimited because it's really governed by what are the different types of crystals that you're growing in the system, what are the morphologies of those crystals, what is the population density of the crystals, and how big are they growing. An example on the left here, this shows a Formica glass ceramic where you can see the liquid matrix here and then this kind of house of cards type of crystal structure that forms. You can see it zoomed out a bit more on the right here for a mica glass ceramic. These are like needle-shaped crystals here that form this very strong, very tough network because let's suppose that we want to break this glass ceramic. In order to break the glass ceramic, we have to propagate a crack through the material here. And every time the crack encounters an interface between the glassy matrix and the crystal, the crack either needs to deflect around the crystal, which means that it takes more energy to propagate the crack, or it needs to open up a new crack every time that it encounters a new phase. In either case, that means that it takes more energy for the crack to propagate, which means that the fracture toughness of the glass ceramic is quite a bit higher compared to the fracture toughness of the glass itself, because in the glass itself, there aren't any phase boundaries. These examples on the left and the right are both through bulk nucleated glass ceramics, where we use homogeneous nucleation and subsequent crystal growth of the homogeneously nucleated system. You can also have surface nucleated glass ceramics, and that's what's shown here in the middle. This is a surface nucleated, this shows surface nucleated lucite and a lucite apatite glass ceramic. These can be useful, for example, for dental applications. Most glass ceramics that are used in industry are bulk nucleated, but there are some that are surface nucleated as well. This table, which is table 4-2 from the book, shows just a few example glass ceramic compositions and some of the properties before and after the ceramic process. You'll notice that a lot of these are lithium silicate based systems. So lithium silicate is actually a really good base system for having good liquid state properties for forming the initial glass forming liquid into the glassy state, but then being able to control the nucleation and crystal growth processes. This first one, you can see that we have a thermal expansion coefficient in the glass, which is 84 times 10 to the minus 7 per degree C, versus the glass ceramic is 113, so the CTE actually goes up. The big advantage, though, in the glass ceramic is that the softening point is dramatically higher in the glass ceramic compared to the glass because of the incorporation of those crystals. And it's also leaving behind a silica-enriched glassy matrix where most of the lithium is going into the crystals. This first one has the CTE going up. In the second row, the CTE is actually going down in the glass ceramic compared to the glass. And a really interesting one is this one on the fourth column here, right in the middle. This is a lithium magnesium aluminosilicate glass ceramic. The CTE of the glass is 63.4 times 10 to the minus 7 per degree C. And with the glass ceramic, the CTE is almost zero. So this is actually very useful for using as a material where there is a huge thermal variation across the body. So for example, in a glass ceramic cooktop, where if you've got the burner on one part, the cooktop can be very hot, while it's at room temperature at the other end of the ceramic cooktop. And so this glass ceramic material is actually an excellent material for use as a glass ceramic cooktop, both because of its near zero thermal expansion coefficient as well as its stoichiometric softening point, which is around 1,000 degrees Celsius. It's also possible to have glass ceramics with a negative CTE, as shown in the next row. But in any case, you can see that there are some major advantages both in the thermal properties of glass ceramics as well as the mechanical properties. Now, glass ceramics were originally discovered by Dr. S. Donald Stookey from Corning Glassworks. This was back in the 1950s. And he discovered these by accident. He put some glass in a furnace, set the temperature to be at something like 600 degrees Celsius, went home for the night, came back, and was surprised to see that the temperature was actually quite a bit higher, something like 900 degrees Celsius. He opened the furnace expecting to find a molten mess in the furnace and was surprised to see that there was this kind of white body that was inside the furnace rather than having a molten mess. And so he got his tongs, took it out, set it on the table in his lab. So that was mistake number one, having the wrong furnace on his temperature. Mistake number two was he accidentally knocked it off the table onto the concrete floor and noted that instead of it breaking, it actually bounced off of the floor. And Don Stookey, being the excellent scientist that he was, did a lot of studies to understand what was it that, or how did he obtain this glass ceramic material. So he studied about the nucleation crystal growth processes, how to control the development of the crystalline microstructure within the glassy state, but also what was the impact of that microstructure on properties. And so Don Stookey is known as the father of glass ceramics for very good reason. Even though his initial discovery was accidental, he used his outstanding scientific background to really understand the fundamentals of the thermodynamics and the kinetics of glass ceramic formation and the impact of its microstructure on the properties that we cared about. Don Stookey is the inventor of Corningware. Probably most of you have Corningware glass ceramic cookware in your homes. This is glass ceramic cookware that has superior thermal performance and superior mechanical performance because of the incorporation of this crystalline microstructure in the glassy matrix. And so this was a huge commercial success for Corning because of this high strength, high toughness, low coefficient of thermal expansion materials. The downside of Corningware is that it is optically opaque. It is optically opaque because every time visible light encounters an interface between two phases with two different values of the refractive index, there is scattering of the light at that interface. And with glass ceramics, having the crystalline microstructure within the glassy matrix is good for mechanical properties, but it can compromise the optical transparency of the base glass, because if you introduce crystals into the microstructure, every time the visible light encounters that interface between the glassy matrix phase and the crystal phase, it sees a different refractive index that leads to scattering of the light. And in the case of Corningware, there's so many crystals that are at least as large as the wavelength of visible light that basically all of the light gets scattered. It's scattering at all wavelengths, and that's what gives these glass ceramics their white color. Now, as a great recognition of Stookey's accomplishments, both scientifically and from a technological point of view, Dr. Stookey was awarded the National Medal of Technology by President Reagan back in the 1980s. And if we want to make, let's suppose that we wanted to make a glass ceramic transparent, the way to do that is to keep the crystallite size small compared to the wavelength of light, such that if the wavelength of visible light is passing through our microstructure, what it sees is an average of the refractive index of these much smaller phases, as opposed to seeing an interface between phases. And that's what was done here with this Corning Visions cookware. The Corning Visions cookware also has excellent thermal properties, really good mechanical properties as well, not quite as good as Corningware, but still quite good. The difference is that the crystals here are nano-sized so that they're much smaller compared to the wavelength of light, the wavelength of visible light. So when visible light passes through this, it sees an effective average refractive index, and therefore we maintain optical transparency. The reason for the brownish color here is that the Visions cookware uses titania as a nucleating agent. Titania is an oxide that's added to the system to help control the nucleation process, and it also gives it this brownish color. And so having these smaller nano-sized crystals helps to enable optical transparency. If you get a chance, I won't show it here, but check out the TV commercial that Corning had for Visions cookware, where they're actually melting a traditional aluminum sauce pot inside the Visions cookware pot and then pouring it out at the end. What are some other applications of glass ceramics besides cookware? They're also used for smooth cooktops. So in this case, the glass ceramics are used because of their superior mechanical properties as well as their thermal properties. So these are rather ubiquitous now in cooktops. Glass ceramics are also used in dental implants and repair. This has a number of advantages compared to the older style metallic dental implants. Glass ceramics can be designed to have mechanical hardness and strength and toughness that is on par with natural teeth. And they can also be designed to have coloring that is very similar to that of natural teeth, including this kind of natural variation in color where teeth are actually slightly more off-white towards the root compared to towards the tip of the tooth where they're whiter, and that can be mimicked using glass ceramics as well. Glass ceramics are used for space shuttle tiles because of their excellent thermal and mechanical properties. They're also used in missile radome. So they are used across many different industries. Glass ceramics can also be used as an artistic medium. And in fact, if you go to the Palmer Museum here at Penn State, you'll see some of this work by Mary Van Klein, who is a wonderful artist who uses controlled crystallization in glasses by focusing lasers in certain parts to induce localized crystallization. That localized crystallization leads to scattering of light, and she can put these beautiful images. This one on the left, this piece is called Healing Passages of Time, and the one on the right is called The Listening Point. So it actually can be used to create some beautiful art. Glass ceramics can also be used to make photochromic glasses. So photochromic glasses are such that they will precipitate silver halide crystals in response to UV radiation. So if you've got spectacles that have these lenses in them, if you are indoors where there is very little UV radiation, they will be clear. If you go outside where there's more UV radiation, they will darken as a result of formation of silver halide crystals. And the cool thing about photochromic glasses is that this process is reversible. These crystals will go back into the glassy state upon removal of the UV exposure, and so you can transition back and forth between a clear state and a darkened state. Um, and finally, I'd like to end this with just a brief bio of Dr. Stookey. He was a native of Hay Springs, Nebraska. He went to Coe College, which is in Cedar Rapids, Iowa. He is best known for his accidental discovery of glass ceramics while working at Corning Glassworks back in 1953. He is the inventor of Corningware, a very highly successful line of consumer products sold by Corning, and a prolific inventor. And he was also responsible for the discovery of photochromic glasses and awarded the National Medal of Technology by President Reagan in 1986. I had the pleasure of meeting Dr. Stookey before he passed away in 2014. I met him in 2013. He was in his late 90s at that point. I think he was 98 years old. He came to visit us at Corning, and he always put a big emphasis on people development and training the next generation of scientists. And that was evident even at 98 years old. He wanted to know, what we were doing. He was very excited about the work, and he even came with a list of things that he wanted us to work on. So being able to meet him is something that I will always cherish. All right, this is just a brief overview of glass ceramics. Obviously, we could spend an entire course just on glass ceramics themselves. I hope you enjoyed this overview, and next time we are going to move on to Chapter 5. We're going to get into the structure of specific glass systems, starting with silicate glass systems. All right, thanks for watching, everyone. I will see you next time.